So as we've just discussed, using the first derivative as a direct estimate of the slope is termed Euler's method. So I can write that phi is equal to f, or the slope is equal to some function f of I, f at x of I, y of I. If we plug this back into our differential equation, we end up with y of I plus 1 is equal to y at I plus our slope, which is now f of x I, y I, multiplied by h. And this is pretty simple to carry out. But what's more important is that we take a look at the errors. So when we use numerical solutions to solve differential equations, we normally have two errors that arise. And the first is a truncation error, or discretization error. And this is caused by the method of the technique to estimate y. And the second is a round-off method. And this is caused by a limited number of significant digits. So, if we look at the truncation errors, we have two types of truncation errors. The first is a local truncation error, which is caused by the application of the method over a single step, and the second truncation error is called the propagated truncation error. And this results from approximations that are produced during the previous steps. And the sum of these two is termed the global truncation error. Now we can use the Taylor series again to provide some insights about these errors. So, recall that we had dy by dx, or y prime, is equal to f of x y, where y prime is equal to dy by dx, where x is our independent variable and y is our dependent variable. Now if the solution has a continuous derivative, we can represent this with a Taylor series. So y of I plus 1 is equal to y of I plus y of I prime, the derivative of y, multiplied by our step h, plus the second derivative at I, h squared over 2 factorial, and we can carry on all the way to some nth order. N factorial multiplied by h to the power of n, plus another remainder term. Okay, so here h is equal to x of I plus 1 minus x of I, and r of n is equal to y to the power of n plus 1 divided by n plus 1 factorial at some average value between x of I plus 1 and xi, multiplied by our step size to the power of n plus 1. Now, since y prime is equal to f of xy, we can resubstitute this back into our Taylor series to get y at I plus 1 is equal to y of I plus f of xy multiplied by h plus f prime xy over 2 factorial h squared all the way to f n minus 1 over n factorial h to the power of n plus some error term of order h to the power of n plus 1. So here we can see that the truncation error, or the local truncation error, is proportional to h to the n plus 1. And the truncation error arises because we truncate the other terms of the Taylor series in our Euler approximation. If you recall, the Euler approximation just uses these initial two terms. So in other words, the truncation error, ET, is equal to f prime at xy over 2 factorial multiplied by h squared plus something of the order n plus 1. And where h is really, really small, this reduces to our approximate error f prime at xy multiplied by h squared over 2. In other words, the approximate error is proportional to the step size squared.